Hello there and welcome back to the Sleep Science. Tonight your eyes adjust slowly, not to darkness, but to a faint, impossibly ancient glow. It's not a lamp, not a candle, not even the sun. It's the first light of the cosmos, streaming toward you from a time before you, or here, even meant anything. In your mind's ear you can almost hear it, a thin, shimmering hiss whispering through the black. You're floating in the silence of deep space, and every direction looks the same. Endless black velvet sprinkled with pinpricks of something you've only just begun to notice. You probably won't survive this trip. Don't worry, neither would anyone else. But at least it'll be beautiful. So, before you get comfortable, take a moment to like the video and subscribe. But only if you genuinely enjoy what I do here. Go ahead and post your location and local time in the comments. Someone somewhere might be drifting off to this at the exact same moment you are. Now dim the lights, maybe turn on a fan for that soft background hum, and let's ease into tonight's journey together. You're hovering around 380,000 years after the Big Bang. Give or take the odd millennia, cosmic watches aren't particularly precise. Until now, the universe has been an opaque, blinding soup of free electrons and photons smashing into each other like toddlers in a bouncy castle. The light existed, sure, but it couldn't get anywhere, trapped in a fog so thick it would make a London pea souper look like a crisp autumn morning. Historians still argue whether the term cosmic fog sounds romantic or just damp, but the physics is straightforward. Every time a photon tried to travel, it immediately collided with an electron, scattering like a nervous party guest, changing conversation topics mid-sentence. This era is known as recombination, though the name is misleading. Nothing's recombining from before, because before this moment, atoms as we know them didn't exist. The temperature finally cools to about 3,000 Kelvin, still hotter than your oven on its best day, and electrons at last settle down into orbits around protons, forming neutral hydrogen atoms. With the electrons bound, photons can at last travel freely, and the first light bursts across the universe. Imagine the lights coming on in a cinema after a very long, very confusing trailer. You can still see this light today. It's the cosmic microwave background, CMB, a faint afterglow that now bathes the entire sky in a gentle, uniform whisper. In the 1960s, Arno Penzias and Robert Wilson accidentally detected it while trying to get rid of what they thought was bird droppings on their radio antenna. Spoiler, it wasn't bird droppings, it was the echo of creation. Fringe fact for you, they actually cleaned the antenna thoroughly, convinced it was pigeons living inside, before realizing they just scrubbed at the oldest light in existence. You drift forward, letting this newborn light stream around you. Its photons have been traveling uninterrupted for nearly 14 billion years. No rest stops, no coffee breaks. They don't tire because they don't age. Time doesn't work on light the way it works on you. You reach out purely in imagination and try to catch a photon, but the moment you think you've got it, it's already gone, racing away at 299,792,458 meters per second. You wonder who first tried to measure that speed, and we'll get there. But for now, it's enough to feel it rushing past, unstoppable. The sensation is oddly calming. You're not just looking back in time, you're inside the very moment when the universe became transparent. Before this, there was no seeing, only being. After this, there will be stories, shadows, and eventually, the small, warm glow of a lamp on a desk in some far-off human's home. Even here, there's debate. Historians still argue whether the very first visible light in the universe was actually visible to human eyes, or whether the redshifting over billions of years has left us with something more ghostly than glimmering. But debates aside, this is the origin point for every sunrise, every flashlight beam, every flickering neon sign promising open at 3 a.m. You float in that moment a little longer. The silence isn't really silent. The CMB hum is faint but ever-present, like the universe's own tinnitus. It's the background track of reality, A reminder that every photon has a story and they all began here, bursting free into a universe that, until this instant, had never been able to see itself. You leave the first glimmer behind, gliding into an era so strangely quiet it almost feels like the universe is holding its breath. This is the so-called cosmic dark ages, which sounds far more dramatic than it looks. There's no light for your eyes to catch, at least, not the kind you recognize. The newborn photons from recombination still streak through space, but everything else is utterly black, as though the universe has drawn the curtains and gone to bed early. Here's the weird part. There is light in this time, plenty of it, but it's stretched far beyond the visible spectrum, down into long, lazy radio waves and infrared hum. Your retinas wouldn't stand a chance of picking it up. The only way you see anything here is if you turned into a telescope tuned for microwaves, which, to be fair, would make wearing sunglasses even more awkward. Historians still argue whether the term Dark Ages misleads the public into thinking nothing happened here. In truth, quite a lot was brewing, just not in any way your eyes could appreciate. Hydrogen and helium swirled in massive, invisible clouds, slowly condensing under gravity's patient pull. There were no stars yet, no galaxies, no planets, just cold, dense patches growing denser. You could drift for billions of kilometers and never pass a single glowing speck. A mainstream fact here. During this period, the universe cooled from that earlier 3000 Kelvin down to a frigid few tens of Kelvin, cold enough that, if you could stand still long enough without breathing, or, freezing solid instantly, you'd blend right in with the cosmic background. And for a fringe twist, some theorists speculate that in these silent, starless eons, there could have been massive dark stars made not of hot gas but of dark matter, glowing faintly in wavelengths we've yet to detect. Others call this pure fancy, but the idea of enormous, invisible orbs lazily drifting through the black is oddly comforting. You float between the cold hydrogen clouds. Time becomes meaningless. If you move in any direction, the scenery, or lack thereof, doesn't change. It's like wandering through the world's largest unlit warehouse, with the floor, ceiling, and walls all missing. This is the kind of place where your mind starts to play tricks. Photons are flying past you from recombination, yet they don't so much illuminate as whisper we're still here. Without stars, the universe is eerily uniform. No shadows, no contrasts, no reason to turn your head. You wonder how long it will last. The answer, roughly 100 million years. Yes, million. It's a long wait for sunrise. During that time, matter clumps together under gravity, forming the seeds of the first stars. Hydrogen atoms meet and pile into larger clouds, their centers growing denser and hotter until they'll one day ignite. You can almost feel that slow, building tension, like the quiet moment before an orchestra's first note. Every so often you catch the faintest ripple, not of light, but of density. These are tiny variations left over from the Big Bang, slightly thicker patches of matter surrounded by slightly thinner ones. They're the reason the universe didn't stay perfectly smooth and featureless forever. Without them, gravity would have had no foothold, no way to collect gas into star-forming knots. It's like baking bread, no lumps, no loaf. Historians still argue whether any kind of pre-stars or unusual energy phenomena briefly lit the darkness before the first true stars. If they did, the evidence is faint and buried under eons of cosmic noise. What's certain is that once stars finally flare into being, the dark ages will end in spectacular fashion. Until then, you just float. It's a strangely serene experience. No danger, no glare, no need to squint. If you've ever been in a pitch-black room with your eyes open long enough that you start to wonder if you're still awake, you know the feeling. Except here, that sensation lasts for 100 million years. Somewhere far ahead in time, light is gathering its forces. Somewhere ahead, hydrogen will collapse, ignite, and roar into brilliance. But for now, you're suspended in the calmest night the cosmos will ever know, waiting for a dawn that hasn't even begun to think about arriving. You feel it before you see it, a subtle change in the darkness, a rising hum in the emptiness around you. After 100 million years of nothing but cold hydrogen clouds and the occasional existential thought, the first stars finally switch on. It's not like a polite sunrise creeping over a horizon. It's more like someone plugged in the universe and forgot to check the wattage. The moment is called cosmic dawn, and it's spectacular. Massive stars, truly massive, dozens or even hundreds of times the sun's mass, ignite in blinding ultraviolet fury. They're nothing like the gentle yellow star you know today. These are short-lived titans, burning hot and bright, with lifespans measured in a few million years. Compared to them, our sun is basically a candle at a birthday party. You watch as their light cuts through the hydrogen fog, ionizing it, blowing electrons off atoms like an enthusiastic kid scattering Lego bricks. This phase is reionization, and it sweeps through the universe in great expanding bubbles of clarity. Historians still argue whether the first stars alone caused it, or whether young galaxies and voracious black holes joined in the effort. Either way, the light transforms everything, turning the once murky cosmos into something that finally has depth, contrast, and texture. Mainstream fact for you: these first-generation stars are called population III stars. They were made almost entirely of hydrogen and helium, with virtually no heavier elements, no carbon, oxygen, or iron. Without those metals, they behaved differently, fusing fuel at extreme rates and ending in titanic explosions. None of them survive today, but their fingerprints linger in the chemistry of later stars. And here's the fringe tidbit. Some astrophysicists speculate these ancient giants may have collapsed directly into black holes, so massive they seeded the monsters we find in galaxy centers today. In other words, cosmic dawn might have set the stage for every supermassive black hole you've ever heard of or feared. From your drifting vantage point, you can see clusters forming, gravity pulling newborn stars into small, shimmering gatherings that will one day grow into galaxies. The sight is almost too much to take in. After so long in perfect darkness, the sudden blaze leaves you dizzy. It's the universe's first attempt at glamour. One particular star catches your eye, or rather, your entire field of vision. It's so luminous it would make the sun look like a dusty bulb in an attic lamp. This star's light races outward, some of it destined to cross billions of years before landing in the sensor of a human telescope. Most of it, though, will scatter, be absorbed, or get swallowed by dust, turning the universe into a sprawling light-and shadow painting. Historians still argue about exactly how quickly these first stars formed after the Dark Ages ended. Did the light begin in small patches that slowly overlapped, or was there a sudden, widespread ignition? The data we have is like trying to reconstruct a fireworks show from a handful of blurry photos. And while you float among them, you can't help but think how short-lived they are. These early giants burn out quickly, exploding into supernovae that seed the surrounding space with heavier elements, the kind you'll one day find in your bones, your blood, and the metal in your toaster. Every iron atom you've ever encountered was forged in the death throes of a star, possibly one from an era not far removed from what you're seeing now. It's loud too, though you can't hear it in the vacuum. If you could, the detonations would be deep, rolling booms that rattle your ribs. Instead, you watch in perfect silence as light and matter scatter into the void. It's beautiful and a little sad. These stars were born knowing they'd die spectacularly, leaving only their light and their legacy. The darkness will never be quite the same again. From here on, the universe will be stitched with pockets of radiance, each telling a story billions of years long. You've made it to the first true dawn, and the cosmic night will never fully return. You've been basking in the glow of the first stars, but now your attention drifts to the light itself, what it is, how it moves, and how in the world we figured out its blistering speed. It's easy to take photons for granted. They're everywhere, bouncing into your eyes faster than you can think about them. But to measure their pace, that's like trying to catch a cheetah in the dark with a stopwatch you borrowed from someone who's never used one. Light doesn't just go fast, it defines fast. In a vacuum, every photon races along at exactly 299,792,458 meters per second. That's so absurdly quick you could circle Earth 7.5 times in a single second. Yet for most of human history, people thought light was instant. No speed, no lag, just there. Even Aristotle, who usually had something to say about everything, didn't believe it traveled at all. Historians still argue whether ancient Greek philosophers truly debated light's speed or just waxed poetic about it. But we know at least a few early thinkers suspected it might take time to cross space. Unfortunately, the technology to test that hunch wouldn't exist for centuries. A mainstream fact here. Today, we can measure light's speed so precisely that it's actually used to define the meter. Since 1983, the meter has been officially pegged as the distance light travels in a vacuum in 129979245 of a second. In other words, light's speed isn't just a number, it's baked into the very language of physics and engineering. For a quirkier tidbit, did you know that the ancient Chinese philosopher Mozi, 5th century BCE, speculated that light traveled in straight lines and could be blocked or reflected? He didn't measure its speed, but he'd have made a fine lab assistant for Galileo when that time came. You drift in space and imagine an invisible finish line somewhere ahead. Photons from the early stars are screaming toward it, never tiring, never slowing in a vacuum. They don't need gas stations, coffee breaks, or motivational speeches. They simply go. And the wildest part, every single photon, no matter its energy or origin, moves at the same exact speed in a vacuum. Gamma ray, visible light, or lazy radio wave, it's all the same pace. Still, measuring that speed is trickier than you might think. On human scales, it's so fast that Earth is too small to really test it in a simple experiment. Shine a light from one mountaintop to another and you'll get the answer instant. Not because it is, but because the travel time is too short for your clock to catch. Historians still argue whether our first truly solid measurements were flukes of timing or feats of genius. But they all agree the quest to clock light speed led to some charmingly impractical experiments. Ones involving lanterns, rotating mirrors, and later, an entire planet's worth of orbital motion. As you hover, you watch photons race past you, ancient ones from the Big Bang's afterglow, younger ones from the first stars, and even the occasional rogue gamma ray from some distant cosmic explosion. They're all in the same cosmic marathon, but they've been running different courses for different lengths of time. None of them will ever stop unless they're absorbed or scattered. It's the ultimate endurance run. And here's a strange thought, from a photon's own perspective. If such a thing could exist without time, the moment it's created and the moment it's absorbed happen instantly. No time passes at all in the frame of light. For you, the journey might take billions of years. For the photon, it's zero. Try wrapping your sleepy brain around that before bed. It's the cosmic equivalent of thinking about where socks go in the laundry. Soon, you'll see just how hilariously human our first attempts to measure that speed were. Spoiler, they involved a lot more guesswork and awkward waving of lanterns than you might expect from serious science. But for now, you let the photons stream by, each one carrying the silent message. This is as fast as it gets. You're standing on a windswept hilltop in the 17th century. Well, standing in the loose sense, since you're still drifting through this sleepy tour. Down below, the landscape is dotted with flickering oil lamps, the air smelling faintly of wood smoke and sheep. Somewhere nearby, Galileo Galilei is squinting at you, or maybe just squinting at the dark, which is impressive considering it's not clear he could even see that well by this point in his life. Tonight's entertainment, the very first recorded attempt to measure the speed of light with human reflexes and some moderately wishful thinking. Galileo's idea was simple. Take two lanterns with shutters, place them far apart on separate hills, ideally, and have one person open theirs. The other person, upon seeing the light, opens theirs in return. Measure the delay between opening the first and seeing the second, and voila, light speed. Mainstream fact: Galileo concluded that if there was a delay, it was too small to measure, which is polite scientist speak for yeah, light's fast, and our eyeballs are not precision timing devices. Historians still argue whether he was expecting the delay to be measurable over the tiny distances he used, just a few kilometers, or whether he mostly wanted to prove it was instantaneous. Either way, the result was, needs bigger hills. The quirkier fringe tidbit: some sources claim Galileo performed these tests with assistants who were less than perfectly coordinated. Think of the 17th century version of a slow texter. Add in windy lantern flames, inconsistent shutter movements, and the fact that the speed of light would have crossed that distance in a few millionths of a second, and you see the problem. The human reaction time alone, roughly a quarter of a second, was enough to make the whole thing more comedy than physics. Still, it was a step in the right direction. Galileo at least treated light as a thing with a measurable speed, not an instant magic beam. And his method, flawed as it was, foreshadowed the idea of using known distances and precise timing, something later experiments would refine with far better tools and fewer sheep watching. You hover nearby as Galileo repeats the process. Lantern 1 click, lantern 2 click, stopwatch well, an hourglass running. They're waiting, watching, but the delay is indistinguishable from the time it takes to notice the other lantern at all. You can almost hear Galileo muttering, "Well, that's disappointing," in Italian. Historians still argue whether he abandoned the project entirely after that or continued tinkering in hopes of better results. What's certain is that, within a few decades, other minds would tackle the same problem in much grander fashion, swapping hills for planets and shutters for astronomical timing. But before that leap, you linger here for a moment. The lantern light is soft and warm, the hills stretching away into darkness. The air is cold, but the scene is oddly cozy, a reminder that even the grandest scientific questions often begin in small, humble experiments. You can almost imagine Galileo explaining to an assistant, "We didn't fail, we just discovered human eyes are slow." Up next, the measuring stick is going to get a whole lot bigger, and the timing will no longer rely on quick thumbs and steady hands. Instead, we'll let the entire solar system do the stopwatch work for us. But for now, the hilltop is quiet, the lanterns are dim, and the thought that humans were willing to try and catch light with nothing but a shutter and a glance makes you smile. The hills fade, the oil lamps wink out, and suddenly you're floating far above Earth, peering toward Jupiter. The year is 1676, and a Danish astronomer named Ole Romer is about to become the first person to successfully put a number, well, an estimate on the speed of light. His laboratory isn't a hilltop or a dusty study. It's the entire solar system. Romer spends his nights watching Io, one of Jupiter's moons, slipping in and out of the planet's shadow. Like clockwork, Io should reappear at regular intervals as it orbits Jupiter. But Romer notices something strange. When Earth is moving away from Jupiter in its orbit, Io's reappearance seems delayed. When Earth is moving toward it, Io shows up a bit early. The difference is small, minutes at most, but it's consistent. Mainstream fact: Romer reasoned that the delays were due to light having to travel slightly farther when Earth is moving away from Jupiter. Over months, that extra distance adds up to millions of kilometers, and therefore extra travel time. Using this, he estimated that light takes about 22 minutes to cross the diameter of Earth's orbit. While that's not the exact number we use today, it was a staggering leap forward, proof that light has a finite speed. Fringe tidbit: some scholars suggest that Romer's data was noisy and his exact numbers may have been massaged to fit the idea he was proposing. Historians still argue whether he truly nailed the measurement or simply got lucky with the math. Regardless, the principle was sound, and the astronomical community had to face it. Light wasn't instant. You hover near Jupiter as Io emerges from shadow, its icy surface catching sunlight again. It's hard to imagine, but the moment you see it from here, The light carrying that image has already traveled 500 million kilometers to reach your eyes. On Earth, in Romer's time, telescopes are crude, timing is manual, and yet he's catching a delay of mere minutes in an event that takes place hundreds of millions of kilometers away. Historians still argue whether Romer appreciated the philosophical shock his discovery would cause. After all, if light took measurable time to travel, then seeing anything at all meant looking into the past. Every sunrise, every candle flame, every glance at the night sky, none of it was now. It was all light from somewhere else then. You watch as Romer's data is recorded, calculated, and sent to the French Academy of Sciences. The announcement lands like a small intellectual earthquake. Some embrace it, others resist, clinging to the idea of instant light because it feels more natural. But slowly, the finite speed becomes part of scientific consensus. Drifting beside Io, you catch yourself marveling at the elegance of it all. No lanterns, no stopwatches, just orbital mechanics, careful observation, and a dash of stubborn curiosity. It's the kind of problem you can only solve by letting the cosmos itself do the experiment for you. And as Earth swings around in its orbit, shortening and lengthening that photon path to Jupiter, you can almost hear the unspoken message in Romer's work. Light is fast, but not infinite. The universe has a speed limit. You drift down from Jupiter's realm into the quiet study of a man who never actually measured the speed of light himself, but explained why it moved the way it did. It's the mid-1800s, and James Clerk Maxwell is hunched over a desk, surrounded by pages of dense mathematics that look, to the untrained eye, like the scribbles of someone who fell asleep mid-equation. Maxwell isn't chasing Io's eclipses or waving lanterns on hilltops. He's playing with invisible forces, electricity and magnetism, that scientists had until now treated as separate curiosities. But with a flourish of algebra and a dash of insight, Maxwell unites them into one grand theory, electromagnetism. And tucked neatly into those equations is an unexpected treasure, light itself. Mainstream fact: Maxwell's equations describe how changing electric fields create magnetic fields and vice versa. They predict that these fields can sustain each other in self-propagating waves, electromagnetic waves, that move at a specific speed. When Maxwell calculated that speed from known constants, he found it matched the best measurements of light's velocity. The conclusion was irresistible. Light is an electromagnetic wave. Fringe tidbit: Maxwell himself reportedly said, in a wonderfully understated way, that this discovery was of the highest importance, which is like a chef discovering chocolate and calling it moderately interesting. Historians still argue whether Maxwell fully appreciated that his math had revealed not just the nature of light, but the deep connection between physics and the speed limit of the universe. You float inside the pages of his notes, watching the symbols arrange themselves into something almost alive. The C in his equations isn't just a number. It's the speed of any electromagnetic wave in a vacuum, whether it's a red photon from a sunset or a gamma ray from a distant supernova. The speed of light is suddenly not just an empirical fact, it's a consequence of nature's laws. It's worth pausing here. Before Maxwell, light's speed was something you could measure with planets, mirrors, or clever gadgets. After Maxwell, it became a prediction, woven into the structure of the universe itself. If the constants that govern electricity or magnetism were different, the speed of light would be different too. Historians still argue about whether Maxwell's work immediately convinced the broader scientific community. Some physicists were thrilled, others resisted, preferring to imagine light as a disturbance in some mysterious, luminiferous ether. But the link between electromagnetism and light speed stuck, and the equations went on to underpin nearly all of modern physics. You drift closer to Maxwell himself. He's calm, methodical, and perhaps a bit shy, but you sense the quiet thrill beneath his work. His 4 equations, which he didn't even write in the exact form we use today, will later be called the second great unification in physics. the first being Newton's uniting of the heavens and earth under the same laws of motion. From here, the path is set. Once you know light is an electromagnetic wave with a fixed speed, the next question becomes inevitable. If light's speed is fixed by the laws of physics, what does that mean for objects trying to move faster? That's where a certain patent clerk in 1905 will take things in a whole new, and space-time bending, direction. But for now, the study is quiet, the ink is drying, and C has just stepped out of the shadows to become one of the most important numbers in existence. You step, or rather drift, out of Maxwell's quiet study and into a bustling Swiss patent office in 1905. Stacks of paper, clattering typewriters, and a young man with a mess of dark hair who looks more like a distracted philosopher than a civil servant. This is Albert Einstein, and on his desk lies an idea so radical it will turn the speed of light into something more than just a number. It will make it the ultimate speed limit. Einstein's special theory of relativity begins with two deceptively simple principles. The laws of physics are the same for all observers in uniform motion, and the speed of light in a vacuum is the same for everyone, no matter how fast they're moving. That second part sounds harmless enough until you realize its consequences. If light speed is always the same, then time and space themselves must flex to keep it constant. Mainstream fact. Special relativity predicts that as you approach the speed of light, time slows down for you relative to others, distances contract in the direction of travel, and your mass effectively increases. The faster you go, the harder it is to accelerate further. The mathematics make it brutally clear. Reaching the speed of light would require infinite energy. That's nature's way of saying, nope, not happening. Fringe tidbit. Einstein didn't need fancy experiments to prove this. He built it entirely on thought experiments. One of his favorites was imagining riding alongside a beam of light. Historians still argue whether he first pictured this at age 16 or invented the memory later as a neat origin story. Either way, the result was the same. You can't catch light because from its perspective, there is no catching to do. You drift beside Einstein as he scratches notes in the margin, occasionally looking up at the ceiling as though the answers are hiding in the plaster. He's not thinking of rockets or spaceships yet. He's thinking about clocks, rulers, and how light's stubborn consistency forces the universe into strange contortions. If two observers move relative to each other, their measurements of time and space can disagree, but their measurements of light speed will always match. Historians still argue about the public's reaction in 1905. The scientific world was intrigued, but the general public, for most, relativity was just a word that meant complicated. It would take years, and some help from experimental confirmations, before Einstein's ideas became widely accepted. From your floating vantage point, you imagine pushing a spaceship faster and faster towards see your engines roar. Your fuel burns, but each push gets you less extra speed than before. You'd see the outside universe ticking by faster, while those watching you from afar would see your clock ticking slower. And no matter how hard you try, C remains in front of you, like a horizon that never gets closer. This is where light earns its title as the universe's speed limit, not because it's fast in some arbitrary way, but because it's the maximum speed at which cause and effect can operate. Nothing, not matter, not information, can overtake it without breaking the structure of spacetime itself. Einstein doesn't yet know all the places this idea will lead. He's not thinking about GPS satellites, black holes, or the edges of the observable universe. For now, he's just following the logic of light's constancy wherever it leads. And it leads to a universe where speed has a ceiling, time has flexibility, and space is far more fluid than Newton ever imagined. The patent office hums in the background, papers shuffle. Einstein dips his pen again. Somewhere in those pages, the cosmos has just gained its ultimate rulebook. You're drifting now near something massive, so massive it bends not only your sense of direction, but the very paths that light can take. Below you floats a glowing sphere, the sun, its surface boiling with loops of plasma. You watch a beam of starlight skim its edge and curve ever so slightly, as though it's being pulled by invisible fingers. This is the other half of Einstein's insight, general relativity, published a decade after special relativity. Here, gravity isn't a force in the Newtonian sense. It's the warping of spacetime caused by mass and energy. Light, moving through that warped spacetime, follows the curves, bending its trajectory even though it has no mass. Mainstream fact: this bending of light, gravitational lensing, was famously confirmed in 1919 during a solar eclipse. Astronomer Arthur Eddington photographed stars appearing slightly out of place near the sun's edge, exactly as Einstein predicted. The result turned Einstein into a global celebrity, though historians still argue whether the measurements were as precise as the headlines claimed. Fringe tidbit: gravitational lensing isn't just a neat trick for confirming relativity. It can act like a cosmic magnifying glass. Astronomers today use galaxy clusters as natural lenses to see objects billions of light years away, sometimes spotting galaxies so faint they'd otherwise be invisible. In a way, the universe spies on itself. From your perspective, floating near the sun's limb, you can see the effect in real time. A background star that should be hidden by the sun's glare appears to peak around it, its light path curved like a racing car banking around a turn. If you move farther out, the curvature lessens, but it never disappears entirely. Massive objects leave their mark on space itself, and light has no choice but to follow those bends. Historians still argue about the philosophical implications. If light is simply following spacetime's curves, is gravity really a force at all, or just geometry playing out in 4 dimensions? Either way, you can feel the strange elegance of it. Light, which defines the universe's speed limit, is itself vulnerable to the shape of the road it travels. You shift your gaze toward deep space, where the effect becomes dramatic. A distant quasar's light has been bent into a perfect halo, a so-called Einstein ring, by a galaxy directly between it and you. It's beautiful, but it's also a time machine. The light from different parts of the ring has taken slightly different paths and therefore slightly different times to reach you. You're seeing multiple versions of the same object at once. It's a reminder that the universe doesn't just have a speed limit, it also has scenic detours. Every photon you see has taken the path laid out by spacetime, which means your view of the cosmos is subtly warped at all times. Most of the time you can't tell, but once in a while, gravity's lens is strong enough to make you notice. You drift away from the sun, watching its gravitational grip fade, and think about how this bending effect is happening everywhere, constantly. The night sky you see on Earth is really a distorted, slightly delayed, and often magnified portrait of reality, a truth only light and its stubborn adherence to spacetime's shape can reveal. You've been watching light curve around massive bodies, but now you notice something subtler. Light doesn't always move at the same pace, at least not from your point of view. Out in the vacuum of space, photons always zip along at that sacred 299,792,458 meters per second. But drop them into a different medium, a glass of water, a diamond, or even the atmosphere you're breathing, and they slow down, sort of. Here's the trick. The photons themselves never actually take a coffee break. What changes is the way they interact with the atoms in the material. In transparent substances, photons get absorbed and re-emitted, scattered, or nudged along by the material's electric fields. The result is that the signal, the light wave as a whole, moves more slowly than it would in a vacuum. It's like a relay race where the baton still travels, but it pauses briefly at each runner. Mainstream fact: the refractive index of a material tells you how much light slows in it. For example, water's refractive index is about 1.33, meaning light's apparent speed in water is roughly 3/4 of its vacuum speed. In diamond, with an index of about 2.4, it slows to less than half. That's why diamonds sparkle. They bend light sharply, splitting it into rainbow flashes. Fringe tidbit: in extreme lab conditions, Scientists have slowed light to a few meters per second by passing it through ultra-cold atomic gases. Historians still argue whether calling that slowing light is a bit of marketing flair, since the photons are essentially being absorbed and recreated in the medium, rather than literally dragging their feet. You drift toward a pool of water shimmering in starlight. A beam enters the surface and bends, a perfect example of refraction. It's not just changing speed, it's changing direction because the slower part of the wavefront lags behind, tilting the path. Every time you see a straw looking broken in a glass of lemonade, you're looking at this effect. Colors behave differently too. Red light, with its longer wavelength, often bends less than blue light in the same material. That's why prisms split white light into rainbows. The refractive index varies slightly with wavelength. Historians still argue about who first discovered dispersion, though Isaac Newton gets most of the credit for his careful prism experiments in the 17th century. You let your gaze wander through a diamond, watching light ricochet in tight zigzags before bursting out in glittering flashes. It's easy to forget that what you're seeing is delayed, by trillionths of a second, sure, but still delayed, from what it would be if the diamond weren't there. And that delay, scaled up over cosmic distances and materials, matters. Even the air around you is slowing light ever so slightly. At sea level, the refractive index of air is about 1.0003, which means photons are lagging behind their vacuum speed by just a hair. Over short distances, it's irrelevant, but in precision measurements, like laser ranging or fiber optic communications, engineers have to account for it. From here, you start to wonder, if light can slow down, can it ever speed up beyond c? Physics says no, not in any way that carries information. But that doesn't stop the human imagination from poking at the edges of the rulebook. In fact, that question is about to lead you into the strange territory of faster-than-light dreams, loopholes, and maybe just a few sci-fi-worthy cheats. You've watched light bend, split, and slow, but now you're wondering, can anything outrun it? The answer, according to everything we know, is a resounding no. But that's never stopped physicists from looking for loopholes. After all, the phrase, universe's speed limit, is just begging for someone to see if they can sneak past it without getting a cosmic speeding ticket. Mainstream fact. In special relativity, nothing with mass can reach or exceed the speed of light in a vacuum. As you approach c, your energy requirement shoots toward infinity, which is physics' polite way of saying don't bother packing for that trip. But that hasn't stopped theoretical explorations of exotic possibilities, particles that might always move faster than light, distortions of spacetime itself, and shortcuts that bypass normal space altogether. Fringe tidbit, tachyons, hypothetical particles that would only exist at speeds faster than light, have been proposed in some speculative physics models. They'd have imaginary mass in the mathematical sense, not the it's not real sense. And their weird property would be that they can't slow down to or below c. Historians still argue whether tachyons are a serious avenue of research or just a clever mathematical curiosity. So far, there's no experimental evidence for them. You drift into the realm of the Alcubierre drive, a theoretical concept from 1994 that suggests you could travel faster than light without technically breaking the rule. The idea is to compress space in front of your ship and expand it behind, effectively surfing a moving bubble of spacetime. Inside the bubble, you're not moving faster than light relative to your surroundings. Space itself is doing the moving. Of course, the math requires negative energy, something we don't know how to produce in the required amounts without also collapsing into a very expensive physics paper. Historians still argue whether wormholes, tunnels through spacetime, would allow faster-than-light travel or just rearrange distances so that the journey feels faster. Either way, you'd still be limited by the need to get both ends of the wormhole into position, which somewhat spoils the drama of a quick getaway. You glance over at quantum physics, thinking maybe it has some tricks. There's quantum entanglement, where particles separated by vast distances seem to affect each other instantly. Tempting, but no information can be sent that way faster than light, so relativity keeps its crown. Likewise, certain experiments show group velocities of light pulses appearing to exceed c in special media. But it's an illusion. The actual photons still obey the limit, and no usable signal outruns light in a vacuum. It's almost poetic. The closer you look for a way to cheat light speed, the more the rules fold themselves into place. The limit isn't just stubborn, it's baked into the geometry of spacetime itself. The only true faster you can get is if space itself expands, as it did in the universe's early inflationary phase, when regions of space moved apart faster than light could cross them. But that's space moving, not anything in space, so it's still technically within the rules. You float back into normal space, watching photons whip past. They seem smug, as if they know you can't catch them. Maybe they do. After all, they've been running the same race for nearly 14 billion years without once losing to anything we've built or imagined that could carry a message from a to-be. But you can't help wondering, even if light speed remains the absolute limit, maybe the trick isn't to outrun it, but to make the trip feel shorter. Which brings you to the very human urge to use light not just as a cosmic messenger, but as a clock, one that can tell us where we are when we are, and exactly how fast we're moving without us ever needing to look out the window. You're no longer drifting in deep space. Instead, you find yourself hovering above Earth, but not in silence. There's a faint mechanical hum beneath you. It's the sound of a GPS satellite passing overhead, its solar panels catching the sun's light while its atomic clock ticks with perfect precision. These machines are the unsung poets of the light speed limit, using it to tell you where you are without you even thinking about it. Mainstream fact: GPS, Global Positioning System, works by measuring how long it takes a signal, a form of electromagnetic wave, moving at light speed, to travel from multiple satellites to your receiver. Since the speed of light is constant in a vacuum, that travel time translates directly into distance. By comparing distances from at least 4 satellites, your device triangulates your position anywhere on Earth, whether you're driving in a city or hiking in the middle of nowhere. Fringe tidbit: the GPS system wouldn't work at all if engineers ignored relativity. The satellite's clocks tick slightly faster than clocks on Earth because they're in weaker gravity, general relativity, but also slightly slower because they're moving relative to you, special relativity. The net effect is about a 38 microsecond difference per day, which might sound small, until you realize that if uncorrected, it would throw off your location by roughly 10 kilometers every day. Historians still argue whether early GPS designers truly grasped just how much Einstein's theories would be baked into the system's core. But without those corrections, your Maps app would be a disaster. From your perch beside a satellite, you watch it send out a pulse of radio waves toward Earth. The photons in those waves take about 0.07 seconds to reach the ground, too quick for you to notice, but enough for the satellite's atomic clock to mark the difference between you're on Main Street and you're in the river. Your phone, oblivious to the math, just cheerfully drops a pin exactly where you're standing. Historians still argue about whether GPS is our first true, everyday brush with relativistic physics. Sure, particle accelerators depend on it, and so do astronomers, but GPS is the quiet ambassador of light speed, affects to billions of people who have no idea they're using Einstein in their pockets. You drift lower, watching a fleet of satellites crisscross Earth's night side, their paths coordinated so that no matter where someone is, several are always in view. Some bounce signals between them to improve accuracy. Others share time data with ground stations. All of them rely on the same constant, c, to translate time delay into distance. You glance toward a city below. Someone there just tapped order food in an app, and somewhere else a courier got the job, both trusting that GPS won't put the delivery on the wrong continent. In another corner of the world, a ship is navigating a narrow harbor entrance at night. Somewhere else, A farmer's autonomous tractor is plowing perfectly straight rows. All of it rests on knowing how long light takes to get from point A to point B, down to the billionth of a second. It's a quiet irony that the same universal limit that keeps us from ever reaching other stars in a weekend is also what lets you find the nearest coffee shop without getting lost. Light speed doesn't just govern the cosmos, it maps your morning commute. From here you can see how fragile it all is. Change C, even slightly, and our measurements crumble. But C is stubborn, reliable, relentless. And in that relentlessness, you realize, lies one of humanity's greatest tools for navigating a spinning blue sphere under an endless black sky. From the neat orbits of GPS satellites, you drift outward again, past the moon, past the planets, until the sun becomes just another star behind you. Out here, light's role changes. It's no longer just a helper for maps or selfies. Out here, it becomes a strict warden. Every message, every glimpse, every whisper from one part of the cosmos to another is bound by its speed. You've entered the cosmic speed trap. Mainstream fact: the speed of light sets the ultimate communication limit across space. If you send a message to Mars right now, the delay could be anywhere from 3 to 22 minutes depending on where the planets are in their orbits. Talking to someone on Pluto, that's over 4 hours each way. And the nearest star system, Alpha Centauri, is 4.37 light-years away, meaning a hi you send today won't arrive until sometime in the 2029 calendar. Fringe tidbit: in the 1970s, researchers proposed slow-scan television for deep space probes, essentially sending one image pixel at a time to cope with bandwidth limits imposed by both technology and light's stubbornly finite pace. Historians still argue whether our first interstellar messages will be more like crisp high-definition streams or clunky Morse code transmissions. Given the distances, betting on Morse code might be wise. You hover over the pale blue dot of Earth and think about the vast invisible bubble of light that surrounds it. Every radio broadcast, every radar ping, every Wi-Fi signal leaks out into space at light speed, forming an expanding shell roughly 100 light-years across. Inside that shell, an alien civilization could detect us, if they were listening at the right time, on the right frequency, and happened to have the patience of a saint. Outside that shell, our entire history might as well not have happened yet. Historians still argue whether this delay is a blessing or a curse. On the one hand, it means there's no instant cosmic eavesdropping. On the other, it makes real-time conversation with distant civilizations basically impossible. The same speed limit that binds our physics also binds our curiosity. You turn toward the faint, pinpoint glimmers of spacecraft we've launched: Voyager 1 and 2, Pioneer 10 and 11, New Horizons. Each is sending data home at the speed of light, but home is now many hours of photon travel away. Voyager 1's radio signals take over 22 hours to reach Earth, and by the time engineers receive them, the spacecraft has long since moved on. It's like trying to steer a car with a one-day delay on the steering wheel. Even in more local space, the speed trap is noticeable. Controlling a Mars rover requires careful patience. By the time it executes a command, the moment you're reacting to might be long past. Out in the Kuiper Belt or beyond, you can forget about joyrides. You're essentially mailing instructions to the future. As you hang here, you feel a strange kind of peace. Light's limit isn't malicious, it's just the rules. It forces the universe to have a certain order. No instant changes across impossible distances. No universal simultaneity. The future always arrives one photon at a time. From here, the next step is inevitable. If light takes years, or even billions of years, to bring us information, then looking into the far distance is the same as looking into the past. And some of the light still heading toward you right now began its journey before Earth even existed. You turn your gaze outward, toward the deep sky, where the pinpoints of light are far older than they seem. That faint glimmer over there, its photons have been traveling for billions of years, crossing intergalactic voids to end their journey in your eye. Some of them left their source before Earth was even a twinkle in the Milky Way's spiral arm. Mainstream fact: the light from the Andromeda Galaxy, our nearest large neighbor, takes about 2.5 million years to reach us. That means every time you look at it, you're seeing Andromeda as it was when early humans were just beginning to shape stone tools. Go deeper, and you find galaxies whose light set out 10 billion years ago, long before our solar system formed. Fringe tidbit: some photons are so old that the galaxies they came from no longer exist in their original form, merged, torn apart, or transformed by cosmic evolution. Historians still argue whether catching such light is more like seeing a ghost or opening an ancient time capsule. Either way, what you're seeing isn't now. It's a preserved fragment of then. You drift toward a beam of ancient starlight, its waves stretched redder and redder by the universe's expansion. Cosmologists call this redshift, and it acts like a cosmic speedometer, telling you how far and how fast the source has receded over the eons. The most distant light we've detected comes from galaxies so far away their photons have been traveling for over 13 billion years, nearly the entire age of the universe. Historians still argue about which is more astonishing: that light can travel unimpeded for so long without losing its identity, or that our eyes and telescopes can still detect such faint whispers after so much cosmic wear and tear. From your vantage point, you see it as a grand relay race. Photons leap from a star's surface, dodge through dust clouds, skirt the gravity of passing objects, and finally, after a journey longer than all of human history combined, they land, softly, silently, on a detector in some mountaintop observatory or space telescope. The astronomer looking at the resulting image isn't just studying a galaxy, they're meeting it across a gulf of time. You glance back at Earth and realize this works both ways. Light leaving our sun right now will one day be ancient light to someone else, if there's someone there to catch it. Our starlight is already heading toward distant galaxies, a quiet record of our star's current youth that will arrive long after the sun has faded into a white dwarf. In this way, the speed of light becomes not just a limit but a gift. It lets us see the universe's autobiography written in photons, each page from a different era. Without it, everything would be now, and the story would vanish into a single frame with no depth. As you float among these ancient beams, it's easy to forget that some of them are so faint they deliver just a handful of photons per square meter per second. And yet, those few photons can unlock the history of galaxies, stars, and even the elements that make you up. They are the messengers from the deep past, and they've been traveling toward you for longer than life has existed on Earth. You turn slightly and notice something in the darkness, not an absence of light, but a smudge, a veil. It's not that the photons never left their source, it's that they've been slowed, scattered, or swallowed along the way. You're drifting through one of the universe's great traffic jams, the dust and gas clouds of interstellar space. Mainstream fact: interstellar dust isn't like the dust on your bookshelf. These grains are tiny, often smaller than a micron, and made of carbon, silicates, ice, and sometimes complex molecules. They scatter and absorb light, especially the shorter wavelengths like blue, which is why stars seen through dust clouds often appear redder. Astronomers call this reddening, and they have to correct for it when measuring distances and brightness. Fringe tidbit: some researchers think these dust grains might carry organic compounds, possibly even the raw ingredients for life, between star systems. Historians still argue whether panspermia, the idea that life seeds travel on such grains, is a legitimate theory or just cosmic romanticism. From your drifting position, you can see the effect clearly. A bright star on the far side of a dusty nebula looks dim and coppery, as though you're seeing it through old glass. Move around the cloud and its true brilliance returns. For light, the dust is like a congested freeway. Every photon still travels at sea between collisions, but the zigzags, detours, and re-emissions stretch the journey. Sometimes, the dust becomes part of the show. In regions like the Orion Nebula, scattered light from young, hot stars illuminates the surrounding gas, creating glowing curtains of red and violet. In others, the dust is so thick it hides newborn stars entirely, their light detectable only in infrared wavelengths that slip through the particles. Historians still argue about just how much dust altered our earliest cosmic maps. Before infrared telescopes, astronomers underestimated the number of stars in certain regions simply because the dust swallowed their visible light. Whole clusters hid in plain sight, their photons trapped in long, slow battles with interstellar grit. You drift toward the densest part of a molecular cloud. It's cold here, just a few degrees above absolute zero, and the darkness is almost total. Only the faint, ghostly glow of background starlight leaks through. In time, gravity will pull this dust and gas into tighter knots, and stars will be born here. But for now, it's a place of slow traffic, where the speed of light is less a law of nature and more a reminder that photons, too, can get caught in a cosmic commute. As you ease away, the view clears. The dust is still there, still shaping the starlight, but your path forward is free again. It's a reminder that while light's ultimate speed is fixed, the journey can be lengthened, twisted, and delayed, sometimes for millions of years, before it reaches its destination. And in rare cases, the interaction between light and matter becomes so intense that photons themselves seem to transform, giving rise to something even stranger. That's where you're headed next, to the border between light and matter, where the two are not so different after all. You leave the dusty lanes of the galaxy and find yourself in a lab, well, several labs, scattered across different eras, where light is being pushed to its limits, not in speed but in identity. Here, photons stop being just pure packets of light and start behaving like matter. Mainstream fact: under certain conditions, photons can transform into particle-antiparticle pairs, such as an electron and a positron. This is called pair production, and it happens when a photon has enough energy, typically a gamma ray, and interacts with a strong electromagnetic field, often near an atomic nucleus. The mass of the resulting particles comes directly from the photon's energy, via Einstein's famous equation E equals mc2 equals mc2. Fringe tidbit: in theory, this process could happen in empty space if two photons collide with enough combined energy. Historians still argue whether such photon collisions have been directly observed in the lab, though experiments at particle accelerators like the Large Hadron Collider have gathered compelling hints. From your vantage point, you watch a high-energy gamma photon approach an atomic nucleus. It vanishes in a burst, replaced by two new particles spiraling away in opposite directions, one matter, one antimatter. It's a kind of magic trick where the rabbit really is made out of the hat. In astrophysics, this isn't rare. Around black holes and neutron stars, where magnetic fields are unimaginably strong and photon energies are extreme, pair production happens constantly. It feeds the plasma streams blasting from quasars and can even shape the glow of certain gamma ray bursts. Historians still argue about whether early astronomers fully understood the role of such processes in shaping cosmic light sources. The idea that pure light could become tangible matter challenged the tidy divisions between particles and waves. The reverse is also true: matter can become light. In annihilation, when an electron meets its antiparticle, a positron, they destroy each other, producing photons. This is nature's most efficient recycling program. All the mass becomes energy, no leftovers. You drift closer to a particle accelerator where scientists are coaxing photons into strange states, sometimes slowing them, sometimes coupling them to atoms so tightly that they behave like they have mass. In these polarions, light and matter blend into hybrid particles, moving slower than C even in a vacuum-like environment because they're no longer pure photons. It's here at the border between light and matter that you realize the speed limit isn't just about motion, it's about identity. Light can't outrun itself, but it can change what it is, altering the rules it plays by. The photon that began its life in a star's core might end it as part of an atom, or as the kinetic energy of an electron racing through space. From the cosmic scale to the quantum lab, this dance of transformation ties everything together. The same physics that lets light become matter under extreme conditions is the reason your body is made of stardust, born from the fusion furnaces of ancient stars. And speaking of stars, just as they can give birth to photons, they can also one day fade, taking their light with them. That's where you're headed next, the slow, inevitable dimming of the universe. You leave the bright, bustling laboratories and drift back into deep space, but this time your surroundings feel different, emptier, quieter, as though the cosmos itself is winding down. The stars are still here, scattered like embers, but you can sense their future. Every one of them is living on borrowed time. Mainstream fact: stars burn their fuel through nuclear fusion, and when that fuel runs out, they die. Massive stars go in spectacular supernovae, scattering heavy elements across space. Smaller stars like our sun fade into white dwarfs, dense, Earth-sized remnants that slowly cool over billions of years. Eventually, even those will become cold, dark husks called black dwarfs. Fringe tidbit: some cosmologists speculate about the degenerate era, trillions of years from now, when the last faint white dwarfs will radiate away their remaining heat, leaving the universe lit only by the occasional flash of a decaying proton or the collision of two dead stars. Historians still argue whether anyone, or anything, will be around to witness that darkness. From your drifting viewpoint, you fast forward the clock. Galaxies thin as their brightest stars explode, leaving behind long-lived red dwarfs, each barely more than a steady ember. Over more billions of years, even they sputter out. The sky loses its glitter, turning into a vast, dark canvas dotted only with the faint heat glows of the cooling remnants. And light itself, it doesn't stop existing, but it becomes scarce, its sources few and far between. The photons that do emerge travel unimpeded through an ever-expanding universe, redshifting into oblivion as space stretches them to longer and longer wavelengths. Eventually, the light is so faint and cold it blends into the background, indistinguishable from the universe's own dark hum. Historians still argue whether the heat-death scenario, where everything reaches a uniform, cold equilibrium, is inevitable, or whether some exotic physics could reignite the cosmos in the far future. The melancholy truth is that, under our current understanding, the era of brilliant starlight is just one chapter in a much longer story, and it's already well underway. You drift past a galaxy where the last supernova has just faded. The surrounding space is silent, not because there's no sound in space, but because even the events that could make light are now rare. The once busy lanes of photons racing past you are now almost empty. It's sobering to think, someday, the universe's speed limit won't matter much at all, not because something has surpassed it, but because there will be so little left trying to race. The great highway of light will remain, but the traffic will be gone. Still, you're not quite ready to end in darkness. Light's limit also lets us peer back in time, across billions of years, to see moments when the universe was young and bright. And you're about to take one of those journeys, riding photons all the way backward to the dawn of galaxies themselves. You turn away from the dimming future and let your gaze fall on a single speck of light, impossibly far away. It's faint, stretched deep into the red by the universe's expansion, but still carrying a story billions of years old. You decide to follow it back, riding it in reverse along the thread of time it has woven through space. Mainstream fact: because light travels at a finite speed, the farther away we look, the further back in time we see. Telescopes like the Hubble and James Webb Space Telescope function as time machines, capturing light that left its source billions of years ago. The most distant galaxies we've observed date to less than 1 billion years after the Big Bang, their light traveling over 13 billion years to reach us. Fringe tidbit: Some astronomers hunt for cosmic dawn galaxies by targeting the faint glow of hydrogen atoms in the early universe, a signal stretched to radio wavelengths by cosmic expansion. Historians still argue whether our current instruments are catching the real beginning of star formation or just the bright tip of a much dimmer iceberg. You follow the photon back past empty stretches of space, skirting galaxy clusters whose gravity bent its path into a slightly different direction, a cosmic lens without the photon ever knowing it. You pass by massive stars that lived and died long after the photon began its journey, their light joining the great river flowing toward the future. It's strange to think, this single photon began its trip before the Milky Way existed. The universe was younger, denser, and more chaotic. Galaxies were smaller, collisions more frequent, and the light was bluer, shorter in wavelength, before eons of expansion stretched it into the faint red glimmer you're chasing. Historians still argue whether any single photon can tell the whole truth of its era. Dust, gravitational lensing, and the slow fade of cosmic background radiation all add distortions. But even imperfect, each photon is a witness, carrying a memory of where and when it was born. You ride the photon through its origin galaxy, a knot of young stars surrounded by clouds of gas glowing under their ultraviolet light. This is not the tidy spiral of the Milky Way. It's a ragged, turbulent place shaped by constant mergers. Somewhere in that chaos, a massive star throws off a burst of energy, and a photon springs free, racing into the void. That photon is the one you've been following. From here, you could keep going, past the first galaxies, back through the cosmic dark ages, all the way to recombination and the release of the cosmic microwave background. But for now, you stop, holding on to the thought that every night sky is a layered map of time. Some stars you see are neighbors, their light only years old. Others are ghosts from an age when Earth wasn't yet born. The speed of light doesn't just limit how fast we can travel, it's what allows us to see the universe's history at all. And in rare cases, with the right experiments, we can even slow that light down so much that we can watch it crawl instead of race. That's where you're headed next, into the strange laboratories where the cosmic speed limit is politely ignored, at least for a moment. You step out of cosmic history and into a windowless lab, the kind with humming racks of electronics and air so still you can hear the soft tick of cooling metal. In the center, a beam of light hovers in the air, except it's not racing away at 299,792,458 meters per second. It's barely moving at all. You've entered the strange world of slow light experiments. Mainstream fact: in certain materials, light's group velocity, the speed at which a pulse of light energy moves, can be reduced to a crawl. In 1999, physicist Lin Hao and her team slowed a light pulse to just 17 meters per second by passing it through an ultra-cold cloud of sodium atoms. Later, they stopped light entirely for a fraction of a second, storing it as an atomic excitation before releasing it again. Fringe tidbit: some of these experiments use a quantum optical trick called electromagnetically induced transparency, where a control laser changes the way atoms absorb and re-emit light. Historians still argue whether stopping light is the right term, since the photons are effectively transformed into a different form of energy rather than literally frozen in midair. From your vantage point beside the glowing sodium cloud, you watch a pulse of light, just a faint blip, slide into the mist and slow down as though it's suddenly trudging through deep snow. Its shape stretches, its front edge advancing in slow motion, until it disappears entirely into the atomic cloud. A moment later, it re-emerges, resuming its full cosmic sprint as if nothing happened. It's important to note, this doesn't break the universal speed limit. Even here, the individual photons between interactions move at c. It's the signal that's slowed, thanks to countless delays from atom-photon interactions. Information and causality remain firmly in Einstein's safe zone. Historians still argue about the practical uses for slow light. Could it lead to optical buffers for quantum computers? Better data storage in photonic systems? Or is it mostly a spectacular physics party trick? Whatever the answer, the ability to make the universe's fastest traveler crawl like a turtle is a testament to how much control we've learned to exert over nature's most fundamental messengers. You drift over to another lab table, where researchers are doing something even stranger, creating slow light in solid crystals, where it can be stored for minutes instead of fractions of a second. These are the beginnings of light-based memory, where information encoded in photons can be held and retrieved later, potentially revolutionizing secure communication. It's almost funny to think that the same constant that defines the speed limit for the entire universe can be locally overruled by clever arrangements of atoms and lasers. But deep down, the rule hasn't been broken. Light's fundamental nature is untouched, just temporarily tangled up in the lattice of matter. From here, the next step is to take the thought experiment to its personal extreme. We've seen the first light, the slow light, the bent light, and the dying light. Now you're going to imagine catching the last photon you will ever see, the final flash your eyes will register before darkness takes over for good. You're alone now, floating in a darkness so deep it feels endless. The stars are gone, not just hidden, but truly gone. The universe has grown cold and silent, its great furnaces extinguished. In this emptiness, light is rare, a fleeting currency. And then you see it, a single photon, your last. Mainstream fact: in the far, far future, trillions upon trillions of years from now, the universe will have expanded so much that any remaining light will be stretched to wavelengths so long, and energy so low, they'll be undetectable to any eye. Even before then, the death of the last star will mean no new visible photons are being born, leaving only the fading echoes of what once was. Fringe tidbit: some cosmologists theorize about quantum fluctuations in the vacuum that might, on inconceivably long timescales, produce brief flashes of light even in a dead universe. Historians still argue whether these could ever be detected, or if they'd vanish into the statistical noise of eternity. The photon ahead of you is small, humble, and impossibly old. It may have been born in the final explosion of a dying star, or in the merging of two black dwarfs in the last great light show the cosmos ever staged. It has traveled unimpeded for eons, crossing gulfs of space so vast that every atom it passed is now farther away from its neighbors than galaxies are today. You reach for it, not with your hand, because here you have none, but with your attention, your entire being focused on its arrival. For a fraction of a moment, it is yours. It strikes whatever you are in this far future self, and you see it, if seeing can still be the right word when no one else is left to confirm it happened. Historians still argue whether moments like this, tiny, singular flashes in the darkness, are truly endings or just transitions to states we can't yet imagine. But this photon is the end of a story that began nearly 14 billion years ago, when light first broke free to race through space. The darkness that follows is absolute, but it isn't empty. It is filled with the quiet certainty that you witnessed the entire arc, from the first glimmers after the Big Bang, through the bending, slowing, scattering, and dying of light, to this one final messenger. And in its path was the entire history of the universe, carried not in words or symbols, but in pure motion. You let the moment stretch. No hurry now, time has lost its urgency. The speed limit still exists, though there's nothing left to test it against. Somewhere, perhaps, in ways no human mind can now picture, another beginning might be stirring. If it does, light will once again set the pace.